NASA is the National Aeronautics Space Administration, right? It is the space agency for the US government. Anything the US government pays for that goes up into space, if it doesn't belong with the military, it's going to fall under NASA. Either NASA builds it, funds it, runs it, controls it. So anything going up in space, not with the military, NASA's involved. Now, NASA actually has 10 centers that are spread across the country, and here at JPL, we just happen to be one of those 10 centers. But most people tend to be familiar with the East Coast centers, places like Kennedy Space Center. Anyone heard of Kennedy Space Center before today? Yes, if you guys have ever seen a space shuttle blast off, if you've watched documentary footage of the Apollo, the Gemini, the Mercury missions, all those missions actually launched from that place in Florida, Kennedy Space Center. So that NASA center in Florida, their job is to launch things to space. So 90% of the time when NASA needs to send something to space, we're going to want to launch it from over there in Florida. Okay? So that's kind of their job at the NASA center in Florida, at Kennedy Space Center. Their job is to send things to space for NASA. There's another place in Texas, very famous. It's called Johnson Space Center. Anyone heard of Johnson Space Center before today? Yeah? How about Houston Mission Control? Have you guys heard of that? Yeah, maybe seen that on TV. If you've ever seen astronauts on being trained, sometimes you see the astronauts on a machine, they spin them around really, really fast, and you see their face getting squished back like that. Or sometimes you'll see the astronauts wear a spacesuit. They'll stick them in a really deep tank of water. They refer to it as a buoyancy tank, and then you see them floating around the water like they're in space. That's how they practice doing the spacewalks. Or every time astronauts are in space on TV, they show the room where all the computers are, where they talk to the astronauts in space. You might better know it as Houston Mission Control, right? If you've seen any of those things I just mentioned, all those things are actually in Texas at Johnson Space Center, because their job, train the astronauts, get them ready. Once the astronauts finally make it to space, we start sending signals back and forth, and we talk to people in space. We do all the talking with people in space from that place in Texas at Johnson Space Center. And that's why you notice every time astronauts are in space, they talk to people on the ground. They're always referring to Houston, right? Houston this, Houston that, Houston that problem. And that's because that facility, Johnson Space Center, is just outside of Houston, Texas. So that's actually what they're referring to, right? Now, excuse me, here in California, we're lucky because California, we have 3 of the 10 NASA centers here in this state. We're the only state that has that many. There's one up north by San Francisco. It's just outside of Palo Alto. It's called Ames Research Center. They mainly work with software development. So they develop a lot of the software for all those different things that NASA does. They also have the world's largest wind tunnel there to do a lot of wind tunnel testing as well. Then there's another place north of us towards Palmdale. Anyone here heard of Edwards Air Force Base up by Palmdale? Yes. Has anybody here ever been to the air show up at Edwards Air Force Base? They have an air show there every year, at least up until COVID. If you've ever been up there, you guys might have seen the signs that say Dryden Flight Research Center. That's the NASA center. It's actually part of the base. About 15 years ago, they decided to rename it, though, because some famous guy worked there about a decade before he was chosen to be an astronaut. And then later on, he was chosen to be the first guys to step on the moon. You guys heard of that guy? Yeah, Neil Armstrong, right? So they renamed that facility from Dryden Flight Research Center to the Armstrong Flight Center about 10 to 15 years ago. And today it's mainly known as Armstrong, but a lot of people still know it from its first name, Dryden. So if you've heard of Dryden or Armstrong, it's actually the same place, just different names, but it's the same place, right? Now, and just like when Neil Armstrong used to work there, they work with aircraft development. So they work on things that fly. So they would work on things like the space plane, the hyperjet, or that commercial space aircraft trying to develop that supersonic aircraft thing. That they're doing that over there. So that's their job at that NASA center, is to work on things that fly, right? Then there's this place here in Southern California, Jet Propulsion Laboratory. And here at JPL, we are one of those 10 NASA centers, but we do a different job than any of the other NASA centers. Anybody want to take a guess what you think we might do here at this NASA center? Any guesses? Yes? Build rovers, that's right. Have any of you guys been hearing about robots arriving on Mars for the last 20 years? Yeah. If you've been hearing about robots on Mars for the last 20 years, you might have been hearing about Sojourner, or Spirit, or Opportunity, maybe Curiosity, or the most recent one, Perseverance. If you've heard about any of those rovers, all of those rovers were designed, assembled, tested, built right here at JPL. In fact, on this tour today, we're going to see a full-scale model of the Perseverance rover. That's the one that landed on Mars a little over 2 years ago. And if you've been hearing about something on Mars looking for life and stuff, most likely you've been hearing about this rover. So we'll talk more about that when we see it later on. We'll also get a chance to see the other older rover, Spirit and Opportunity, when we get to our museum. So those are the types of stuff we do here at JPL. Basically, we are the lead robotic center for NASA. We build robots. They come in different shapes and sizes. They could be as small as a CubeSat, the size of a Rubik's Cube. It might have only one experiment in studying atmosphere here on Earth. Or it could be something like this. This is the Cassini spacecraft. Hopefully you've heard of it. The real thing went to Saturn. This is a half scale. The real spacecraft, it was 3.5 stories tall. with all the fuel on it. It weighed over 5 tons. It was one of the biggest things we've ever built. It went all the way to Saturn. Unfortunately, the mission ended about 5 years ago, or like closer to 6 or 7 now. But when the mission ended, the spacecraft, they had a choice what to do with the spacecraft, because as we walk around today, you're going to find out our robot missions here are one-way missions. 99.9% of them are one-way. They go where they go, they do what they do, they either get destroyed in the process or they stay there forever. Like this spacecraft was an orbiter. It orbited around Saturn. Once we had a couple choices: keep flying it until you use up all the fuel, in which case once you use all the fuel, your mission's over, because you can't turn it. If you can't turn it, you can't talk to it. If you can't talk to it, it's over, right? So we had a choice to use up all the fuel, and then afterwards it just floats in space with no control, or do something with it before we run out of fuel. So near the end of the mission, before we ran out of fuel, they turned on every experiment that they had that still worked on it, and they took a swan dive into the planet. And as it fell into the planet, heat and pressure built up and vaporized the spacecraft and completely destroyed it. And in so doing, we got rid of it, and we knew what happened to it, because we didn't want it to run out of fuel and then float in space with no control, because that then becomes a physical hazard for future missions. It could run into things you don't want to run into, and you can't control it. So rather than losing control of the thing, we decided to basically get rid of it, and we dropped it in the planet and destroyed the spacecraft, right? So the real thing is gone. So you're going to find out that's what happens with our orbiters. It doesn't matter what it's orbiting. Eventually, if it runs out of fuel, it's going to eventually fall into whatever it's orbiting. It might take 10,000 years or 20,000 years, but they're going to fall in, right? So these are the types of stuff we're going to be talking about, the robot missions we send out to all these different places. Now, can anybody think of a reason? Why would you want to send a robot to Mars versus sending people? Because you guys have probably been hearing about, like with Elon Musk and all these people talking about, we want to send people to Mars. We're going to colonize Mars. And in the next decades, we're going to have like cities on Mars and stuff like that, right? Well, if that's the plan, then why bother sending a robot to Mars? Any guesses? Mm-hmm.
Test out what?
To test out, right? To see if it's safe, right? Because as humans, we like to think of ourselves as being on top of the food chain, right? We're in charge of everything. We control the world. The reality is that's not quite true, right? We're actually very delicate creatures. Everything has to be perfect for humans to survive, right? If it's too hot, we don't do too good. If it's too cold, we don't do too good. If there's not enough air, we don't do too good. If it's too much air, we don't do too good. Everything has to be just right, right? Well, problem is going to all these things in space. You put humans in the most extreme environments you could possibly put yourself in, right? So it makes it very difficult to go to these different places. And a lot of people don't realize it's actually very hard and takes a really long time to go to these places, because in movies, things always happen within the next 10 minutes. Right, the guy's on Earth, and then after the commercial, he's out on Mars. Right, but in reality, what people don't realize is it takes a long time to get to all these places. It's very dangerous, very difficult. For example, Mars is only close to the Earth once every 26 months. The rest of the time, we're kind of moving apart from each other. We're far apart. So, can anyone take a guess? When do you want to go to Mars? When you're close to each other or far apart? Close to each other, right? Because if you go when you're far apart, it's going to take you twice as long. It's going to be twice as expensive. It's twice as dangerous. So whenever we send these things to visit all these other places in space, we always have to wait until they're close to each other, right? Well, Mars and Earth are only close to each other once every 26 months. So you're going to find out as we walk around today, we only send things to Mars every 2 years, because that's when Mars and Earth are close to each other. The rest of the time, we're far apart. And if you're going to try to chase after it, it's going to take you just as long, the same amount of time as if you just waited until it comes around and then send it. So you might as well just wait, right? So we have to wait until we're close to each other. Well, if we waited until Mars and Earth were close to each other, we use the biggest, fastest rocket we have right now, and we send people into space and we send them to Mars. It actually would take us 6 months at the very fastest to get there. The reality is most of our spacecraft, like the rovers and stuff, usually take anywhere from the fastest 6 months at the longest 10 months. We say on average about 8, right? But in reality, anything longer than 10, they don't even bother. They just wait until the planet comes back around again, and then watch it, right? So if you did it the fastest, assuming you could do the fastest rocket, you could get there fastest, you waited until you're closest, it takes you 6 months to get there. Well, guess what? Once you send those people to Mars, do you think those people can come right back? No. Because once they get there, now the planets are moving apart. So how long do you think they would have to wait before they could come back to the Earth? 2 years, that's right. Because that's how long it takes to go around. So if you send people to Mars, it'll take you 6 months to get there. Once those people get there, they have to wait 2 years for it to go around to even think about coming back, right? Now, when you're ready to come back, how fast do you think it'll take them to come back? Any guesses? 6 months, because that's how long it took you to get there, right? So if that's the fastest you could get there, well, that's the fastest you're going to take to come back. So 6 months to get there, 2 years to go around, another 6 months to come back. So at the very fastest, assuming everything happened perfect, nothing went wrong, you do it at the most opportune time, everything happened perfect, it still will take you 3 years to send people there and bring them back, right? Well, guess what? We've never seen a human stay in space longer than a little over a year. Right now, the record for a human in space is about 400, a little over 400 days, right? So that's not even 2 years. So we've never even seen a human stay in space longer than a little over a year and a half, right? So we're not even sure if a human could actually survive in space for that long if we were to send them to Mars, right? Not to mention, imagine all the things humans would have to bring with them in order for you to survive at Mars. You'd have to bring all your food, your water, your oxygen, right? You have to bring all your supplies with you. I like to refer to going to Mars like space camping, right? Because most people have gone camping before. And imagine when you guys go camping, imagine all the supplies you guys have to bring just to go on a weekend camping trip, right? If you send people to Mars, you're sending a whole team. You're not sending one guy all lonesome by himself. You're sending 3, 4, 5, 6, 7, maybe 8 people. Now you have to bring the supplies not just for one guy, but 3, 4, 5, 6, 7, 8 people, right? You guys heard we discovered water on Mars? You guys heard about that? Pretty cool, because we discovered water on Mars. Now we don't have to bring water. We could just get it there. Because water is one of the heaviest things for you to have to bring. Imagine when you guys go camping, all the water you have to bring, right? That's pretty heavy to lug around. So if you don't have to do that, that makes it so much easier, right? We could just get the water there. And water is made out of what? Anybody remember? Hydrogen oxygen, H2O, right? 2 parts hydrogen, 1 part oxygen put together. You get a molecule of water. Well, perfect. We could separate those 2 things. Now we have hydrogen. We could use that for fuel. Oxygen, hey, that's what we need to breathe. Now we don't have to bring our oxygen. That makes it even easier to get, right? Well, guess what? There's no supermarkets on Mars, right? So you're going to have to bring all your food with you. Well, imagine, even if you didn't have to bring the water or oxygen, you got to bring all the food with you. How much food do you bring like on just a weekend camping trip, right? Imagine now you're camping for 3 years. Imagine a spaceship you'd have to bring just for you to survive for that long, right? Your spaceship's the size of Costco. We don't have anything that big, right? So those are all reasons why we don't send humans to Mars right now. It's just too difficult. It's pretty cool in movies, but in reality, it's pretty hard, right? We don't have the resources. We don't have the capacity. We don't have the ability. We don't even know if you could actually even do it and keep somebody alive for that long. But guess what? Robots, if you build them properly, right tools, right parts, right equipment, they can go almost anywhere, do almost anything. Because robots, they only need one thing for them to work properly. Anybody want to take a guess? What's that one thing robots need to work properly? Way in the back, yes. Want to take a guess? Electricity, that's right. You give it some way to get electricity, right? So you could say it's a solar panel or a battery or some way to get electricity. If you give it some way to get electricity, you build it properly, right tools, right parts, right equipment, it can go almost anywhere, do almost anything. We can even send it to go study the sun, right? Imagine that. Do you think you could send someone to go study the sun with an astronaut? Probably not. Right? You get irradiated, it'd be kind of hot, right? So, but guess what? A robot, you can send it to the sun, and if it gets destroyed, that's okay. We'll send another one, right? But with people, if something happens, well, you're in trouble now, right? So those are some of the reasons why we don't do that. It's just too difficult, too dangerous. We're not even sure we could do it. So we send robots instead. And we send these robots to pave the way for future humans to potentially go to these different places. Like our rover currently on Mars, Perseverance actually has an experiment called MOXIE. I don't know if you guys heard about that. MOXIE takes the carbon dioxide, the actual air on Mars, and separates the carbon from the oxygen. So I tell the kids it's an oxygen factory, right? So pretty cool. And when it first landed on Mars, they actually turned it on, and it worked. It didn't make a lot of oxygen. They equated to like a small sapling, and that's how much of oxygen it creates. So it's not a lot, but the fact that it works is what's important, because the device on the spacecraft right now is this small. If we make that thing, we upscale it, send something the size of a building, we send that there. Well, 10 years from now, we'll have all the oxygen we need for any of those Mars missions when we send them, right? So these robots are paving the way for future humans to be able to visit some of these places as well. So those are the things we're going to talk about while we walk around today. The robot missions we do for NASA. We're not going to talk about space shuttles, space stations, astronauts in space, missions with people and stuff. Those are all things they do in Texas. We're going to talk about the things we do here at JPL, or the robot missions, like the Rovers and Cassini and these things that go all these different planets, okay? different spacecraft hanging around those different regions. Those are the spacecraft JPL has sent to go study those particular planets or regions of space. So the ones you see hanging around the Earth, that's the ones we sent to study Earth. The ones around Mars, the ones Mars, and so forth and so on. Okay. Other things you guys can see over here on this side, there's a moon rock in the little pyramid there. Right next to the moon rock, there's a little shovel. That shovel was actually on a spacecraft called Surveyor. It spent 3 years on the moon. One of the Apollo missions, their job was to go to the Surveyor and remove certain pieces, including this robotic arm that had this thing. When you come over here and you take a look at the shovel, if you look right below it, there's a picture of the astronaut on the surface of the moon getting ready to chop off the arm that this is attached to. So literally it's a picture of this thing on the moon. And when you look at it, you'll notice there's dust on it. That's real moon dust. Okay? Now if you look over here in the center of the room, these are the older rovers we have sent to Mars. The very, very first rover we sent to Mars is the little one you see there. It was part of a mission called Pathfinder. It landed in 1997. They gave the nickname Sojourner to that little rover. So if you've been hearing about the Sojourner rover, it's that one. And that is full scale. That's how big it really was. We like to say it's about the size of a microwave, right? It's pretty small. Have any of you guys ever seen the movie The Martian? Yes, if you've seen the movie The Martian, the astronaut that gets stuck on Mars, he digs up a rover, he cleans it up, he fixes it, he uses that to call back to the Earth. You guys remember that part in the movie? If you remember that part in the movie, it was actually that rover he dug up and fixed, right? So in the movie, it's a major plot point in the movie, because without it, he wouldn't have been able to get rescued, right? So it's supposed to be that rover that he did it to. And in case you're wondering, yes, the real thing is on Mars completely covered and does just like what you saw in the movie, right? Now, this one right here is the Mars Exploration Rovers. There are 2 of these we sent up to Mars in 2004. You might know them better by their nickname. One was called Spirit, the other one was Opportunity. Spirit spent a little over 6 years on Mars. Opportunity, over 14 years on the surface of Mars, right? This is the same size real thing. It looks just like the real thing. This one is just a model, though. There's nothing on the inside. It doesn't move. It gives you an idea of just how big the real thing would be if you stood next to it. So you can see the little one, we say it's the size of a microwave. This one, we like to say it's about the size of a golf cart. Later on, we're going to see the new one, Perseverance. You're going to see that's about the size of an SUV. So it's way bigger than this one. Now, the other difference is both of these are solar powered. And like we talked about, solar panels work great. The problem with them, you need lots of sunlight. And being on the surface of a planet like Mars, well, guess what? Mars has a daytime and nighttime, just like here on Earth. So that tells you that these solar powered rovers, although they only work in the daytime on Mars. And just like here on Earth, there's not enough electricity to keep them running at night, so they actually go to sleep. So these solar-powered rovers only work in the daytime on Mars. At night, they would go to sleep, wait till the morning, they would wake up, they start working again. So it limited what we could do. So with the newer rover, they decided to leave off these solar panels. Instead, we're going to give it the RTG we talked about next door, that radioactive battery. By giving the new one that battery, that new one can work in the day or the night, during the winter or the summer. We don't have to worry about the sunlight or seasons or time of day or anything like that. We have the freedom to do what we want, when we want, for as long as we want. So we'll talk a little bit more about it when we actually see the rover later on. You'll notice above this, there's a gold thing. In a second, when you walk around, you'll notice that gold thing is attached to a really big long arm on a really big giant spacecraft on the other side of this wall. It's called Galileo. It's the one you guys heard about went to Jupiter. It's full scale, same size, the real thing looks just like it. And unlike the other full scales, like these are just models, this full scale, it's actually made out of spare parts and test parts. So Galileo is actually the same size of the real thing, looks just like it, it's even made out of spare parts, and it even weighs the same as the real thing, right? So it's as close as you get to the real thing without actually going out to Jupiter to go see it, right? So now you'll notice all of our spacecraft, just like Galileo, are wrapped up in material either black or gold, like you saw on some of the stuff next door, or like Galileo, it has a mix of gold and black, right? Now, the reason you see all the wrapping on our spacecraft, number one, space is very cold. And although we have heaters on the spacecraft, if you don't trap the heat, it dissipates the space. So literally, it's a jacket. It traps the heat so you can control the temperature of the spacecraft. So that's why you see them all wrapped. Now, the second reason we have it on our spacecraft go very fast in space, anywhere from 25,000 to more than 50,000 miles an hour. The issue is, big things, we could see them, right? So we never run into big things in space. Like people always ask us, how do you dodge the asteroid? We don't. We don't have to dodge it because we know that big asteroid is moving this way. In 3 weeks, if we go in a straight line, we're going to run right into it. So we don't run into big things unless we want to run into them, right? Because from far away, we can already see we're going to run into that, right? So we never run into big things unless we intentionally want to run into them. The problem is we get hit by small things we can't see, right? Things the size of a grain of sand or a pebble. And you might think, big deal, it's the size of a pebble. Well, this little pebble, it's moving in space at 50, 60, 70, 80,000 miles an hour. Some of these particles will move over 100,000 miles an hour. That's moving faster than a bullet. That's moving faster than a missile. if it hits your spacecraft in the right spot, even though it's the size of a grain of sand, it's like a bullet, it will rip right through you. And if it hits you in the right spot, it can destroy your spacecraft, you can disable it and disable your spacecraft, and you could lose your spacecraft. So the wrapping you see, it's like a bulletproof vest. The black stuff is actually made out of Kevlar, so the same stuff they use bulletproof vest here. The gold stuff is called Kapton. That's mainly out of Mylar. Mylar is like the shiny balloons you see at birthday parties. They put a film over it that gives it a gold shimmer, and that's what you see. It looks like gold. Depending on what part of the spacecraft they want to protect, it could be anywhere from a single layer up to more than an inch thick with multiple layers, right? For example, if it's a fuel tank, it's going to be thicker than a side panel, it might be thinner, right? So it just depends on what part you want to protect. Now, the difference in terms of color, things that are far away from the sun, it's kind of cold. You want to draw heat. Dark colors draw heat. Imagine a black car versus a white car parked in the middle of a sunny parking lot. At the end of the day, the black car is going to be a lot hotter than the white car, right? This is going to retain heat. So spacecraft that go far away, we wrap them in dark colors. The dark colors will absorb heat, help keep the spacecraft warm. Things that are close to the sun, it's kind of warm. We want to reflect the heat. We don't want to overheat. They tend to be in gold because light colors reflect the heat. This has a combination because this went far away to Jupiter where it's cold, so we want to keep the spacecraft warm. The problem is certain experiments work better when they're cold. For example, infrared cameras. If you're familiar, infrared cameras look for things that are hot. So the hotter you are, the brighter you are to the camera. The problem is if the camera itself is hot, it sees everything is the same, right? You can't tell the difference. So infrared cameras, you want to keep the camera itself cold. So those portions of the spacecraft, you're going to be wrapped in gold, where other portions of the spacecraft are going to be wrapped in black. And that's why you see combinations on some of the spacecraft, right? So things that are close to the sun, they tend to be in gold. Things far away, they tend to be in black. Or some will have combinations depending on what temperatures we want portions of the spacecraft to be, okay? Spirit, Opportunity, Curiosity, Sojourner, Perseverance, the one that just landed a couple years ago, they were all built in this room. The Voyagers you guys saw in the very beginning, the ones that are all the way to the edge of the solar system, they were built in this room. In fact, if you guys look on the back wall, you guys notice all the emblems on the back? They represent all the successful missions that have been built in this facility, either in this room or the sister room next door, right? So all those have been built here in this facility. Now that's current to about 10 years ago. We just haven't put the new ones on yet. We haven't had an opportunity. Now, right now they're working on the Europa Clipper. This is the spacecraft you heard about that's going all the way to the moon around Jupiter. But before I talk about that, I want to talk about the people in the room. So if you look towards the left center of the room, you'll notice right in front of us over here, there's a guy standing there. It looks like he's trying to take a selfie. And you might have noticed he hasn't moved since we came in. Everybody notice him? Yeah. In case you're wondering what's up with him, that's not a real person. That's High Bay Bob, right? He's a resident mannequin. We have him in here because sometimes we come in, nobody's working, and they want to give you an idea of the way people would be dressed if they're working, right? But you guys are lucky. You came on a good day. We have real live people doing real life stuff. If you look in the far right, you'll notice they're all dressed up just like High Bay Bob, covered from head to toe in a white suit. Everybody see that, right? Right. Now, the reason they're wearing that, this room you're looking at, we call this a clean room. And if you don't know, clean room is a special type of laboratory where we regulate and control the temperature, the humidity, so how much moisture there's in the air, and most importantly, the particulate level in the room. That means how dirty the room is. If you were to go outside and check the air that we were just breathing here in Los Angeles County, normal Los Angeles County air on a normal day is usually more than 1 million particles per cubic foot. What that means is if you had a box 1 foot all the way around, you filled it up with air from just outside, and you counted how many small little particles were floating inside that little box. At the dirtiest, there could be more than 1 million particles floating inside your box, right? Now, this room is called a class 10,000, meaning that if you did the same thing and checked the air in here, there could be as few as 10,000 particles or less in that same 1 foot box. Right? So outside there's 1 million particles, in here there's 10,000 or less in that same space. Now, in case you're wondering, why does it need to be so clean? Well, if we're going to send something into space with potential for life, it's important for us not to bring any with us, right? And the thing is, here on Earth, there's life everywhere. So we want to reduce potential for contamination. So we want to make this as clean as possible to make sure that if we find something wherever we're going, it's really from there. It's not something we accidentally brought with us, right? Now, the other reasons we do this, it's kind of more of a practicality thing. Imagine like when you buy your car, when you first get it, it's all great, but after a year or two, if you don't maintain it, it doesn't work as well, right? So by keeping something clean, we hope to ensure it's going to work the way we want it. It's less likely to malfunction, more likely to be robust and last longer and give us proper readings, right? So those are all reasons why we're trying to keep this clean, because it'll just make it work better, right? Now, the other thing you'll notice is if you look back on High Bay Bob again, there's a black wire attached to the left wrist wrapped around the neck clip of the jacket. Do you guys see it? Okay, if you look at the real people working, like if you look at the person down on the backside over there, the one that's working on the thing, you might notice their wire will be attached to whatever they're working on, right? In case you're wondering what that is, that's actually referred to as a static ground or ground strap. Our bodies build up static electricity. I'm sure everybody shocked themselves grabbing a door handle before, right? Well, a door handle, no big deal. Down here, they're working on computer and electronic parts. If you've ever worked on computers or electronics, one of the first things they'll teach you is to ground yourself first. And that's because as humans, we're like batteries. We build up static charge. And if you don't discharge that static electricity you built up and you start touching electronics like this, you could send a static charge through it and you could short it out and break it. So we don't want any of our engineers touching this thing and shorting it out and breaking it. So to protect against that, we ask them to ground themselves first. And that's what that black wire is you see that's attached to the people right there. They'll clip it to something grounded, a table, a fixture, a wire. It discharges static electricity. That way, when they start handling the spacecraft, touching it, they don't shock it, they don't break it, okay? So that's why you see that. Now, in case you're wondering, well, how do we get this thing in and out of the room if it's so clean? Well, if you look to your left, there's a big, giant sliding garage door. Do you guys see it? Everybody see it? So that opens up to a giant airlock. There's an outside door, there's an inside door, there's a holding room in between. Everything we send out, everything we bring in, it comes through that airlock. If you look directly in front of the airlock, just below us down here, you'll notice there's a bunch of white containers. Some are white with the corners painted burnt orange. Some are gray. There's black containers. There's black containers with yellow lids. There's gray containers, silver ones, right? They come in different shapes and sizes. These are referred to as flight hardware containers. They can be as small as a lunch pail. They can come as the size of a semi-trailer. What's special about these containers? They're air sealed. So once you put your part inside it, you seal it, it won't let any dirty air in or out. Then we get it through that big giant airlock, just like what you see in the movies. We never open both doors at the same time. Okay, so that's how we can bring things in or out of the room without getting the room, the parts, or anything else dirty. Okay. Now, if you stay where you're at, turn around real quick. Take a look at these things you see behind you. The folks on this app can take a look at the posters. The folks on this app can watch these things you see running behind you, the videos. And if everybody stays where you're at, just turn your head to your right. Look at the end of the hallway. You'll notice in the display case, that's a model of what this thing will look like when they're finished, right? So as I mentioned, this spacecraft is called Europa Clipper. It's going to that moon around Jupiter. Hopefully you guys remember the movie, because the movie just mentioned it. Europa is a big giant ice ball in space, basically, right? The outer layer of it is covered in glacier ice. Underneath the ice, there's a giant ocean. And our scientists believe there could be as much as 2 to 3 times as much water in this moon versus here on Earth. And we like to think of the Earth as a water planet, right? So imagine this moon is like a water ball in space. Now that's important because here on Earth, wherever we find water, we find life. And for the past 30 years, NASA has that mantra. You heard in the movie again, they mention it, follow the water, right? So any place in space that has liquid water, we want to go check out. And definitely any place that has liquid water, not just any kind of water, but liquid water. Because here on Earth, wherever we find liquid water, we find life, right? So this moon has a lot of it, so we want to go check it out. Now, the thing is, if you guys remember, all the planets go around the sun, so sometimes we're on the same side, sometimes we're far apart. So we want to visit Jupiter when Jupiter and Earth are closest to each other, right? Well, Jupiter and Earth are close to each other once every 5.5 years. And that moment is going to happen in October of next year. So sometime in October, for about 3 weeks, the Earth and Jupiter are going to be lined up at the most opportune moment that if you launch within that 3-week window, you can get to Jupiter in the fastest amount of time with the least amount of effort, least amount of energy and time and all this, right? So that's when you want to go. Now, it doesn't mean that you can't go after. It's just that if you're late and you go after, it's going to take you longer. It's going to be more difficult, more dangerous, more expensive, all that stuff. So, well, our preference is to launch within that window, right? So they're targeting to launch this by October. Now, although we call this the Europa Clipper, it's not actually orbiting around the moon itself. It's going to orbit around the planet, and that's because Jupiter emits tremendous radiation. To protect it from the radiation, we're not going to orbit around the moon, because if you orbit around the moon, you're in the radiation the entire time. It's going to cook our spacecraft. And if you guys are familiar, radiation is bad for electronics. It'll break it down, right? So in order to protect the spacecraft, it's going to be doing an elongated orbit. So it's going to fly by the moon, the planet, take pictures, take readings. Then it's going to fly by the moon, take pictures, takes readings, and then go way out to protect itself from the radiation. And then it's going to come back in again and dip itself in that region, take pictures and studies, and then go way back out again. So it's going to be doing this big looping orbit. In its main mission, we expect it to do it somewhere close to about 50 times. They're hoping, if they get lucky, up to 50 times studying this moon. Right now, at the closest approach, they hope to get it to within about 20 kilometers off the surface. Are you guys all familiar with the space station? Right, I'm hoping you guys are. Anybody ever seen a space station go overhead? The space station is the largest man-made object currently in space, right? When we send things to Mars, those things are probably going to be bigger. But right now, the biggest things we've ever built is a space station. It's so big you could see it with your naked eye. You don't need binoculars, you don't need telescopes. You could, if it's in the right spot, it goes over you, it looks like a big H, it just goes over your head, right? You could see it. Well, the space station is roughly, depending on where position it is at the time, usually somewhere between 200 and 250 miles off the surface. Right? This thing, when it gets over that moon, at the closest about 20 kilometers, maybe about 16 miles off the surface. So it gives you an idea of just how close this is compared to like other things, right? So it's going to get really close. Now, its main mission is going to be looking for ingredients that point us towards life, right? Think of it this way. In order for life to exist, you need certain elements and certain conditions and certain environmental conditions to be present in order for life to exist, right? Think of yourself as like you're a chocolate chip cookie hunter, right? And you just made it to the kitchen, and you've discovered there's chocolate chips, there's sugar, there's flour, there's baking soda, there's all the stuff that you make chocolate chips. But have you actually found a chocolate chip cookie? You haven't. You've only found all the ingredients necessary for it, right? Life is the same way. Life needs all these different ingredients and stuff, but not just that. It needs them in specific combinations, specific amounts, and they have to be mixing this together in a specific way with a specific environmental conditions to happen in order for life to form, just like that chocolate chip cookie, right? You need all those ingredients mixed in the right combination with all the right environmental conditions to form into your chocolate chip cookie, and life is the same way. So what we're doing is we're going to this moon to look to see if it has all the necessary ingredients to form that thing in the first place. Because the thinking is, if you don't have these ingredients, then the chance of finding life reduces. And if you don't have the ingredients, then you might not even find life in the first place. But if you find all these ingredients there and the right conditions there, then you're just one step away from life existing there in the first place. So could this be a place where their life could be, right? So we're taking the first step in order to be able to determine that, right? So that's basically what we're doing. Yes?
So the next, on Mars, the next rover is going to start doing archaeological kind of digging.
It's actually doing that already right now.
That
Yeah, the Perseverance rover right now. Yeah, though I think what she's referring to is the Perseverance rover that landed about 2.5 years ago is currently exploring for looking for potential signs of ancient life on the surface of Mars. Right? So it's collecting these samples into a test tube that we're later going to collect. I'm going to leave you hanging there because we're going to see it later. I'm going to fill in the details when we go see it.
A little bit deeper than
Yeah. So I'll mention a little bit more when we get there. Okay. So feel free to go ahead and turn around. Let me talk a little bit more. Right. If they finish this on time, they launch this on time. There's no delays. That thing you're looking at literally will be flying on its way to Jupiter sometime after October of next year. That's the real thing, right? Now you'll notice the whole thing is attached to a structure we call a tilt table. It allows us to tilt the entire structure vertical or horizontal, right? So that way our folks can work on it without straining themselves or having a hard time trying to build it. It also allows the entire thing to rotate so they can spin it around and attach the different parts of different parts, a section of the spacecraft without straining themselves, okay? Now you'll notice the big tube part of the body, that's referred to as the main propulsion module. Most people just literally refer to it as the body of the spacecraft. Some people say the main bus because all the big pieces get attached to that. But that's like the body. And if you were to look inside that cylinder part, you would actually find two big giant fuel tanks because most of the volume, most of that space on the inside is actually taken up by two big giant fuel tanks, okay? Now, if you look towards the top of it, there's a thing that looks like a flying saucer. You guys see that? That's actually the high-gain antenna. That's how we talk to it. That's how it talks to us. If you look at the model or the pictures, that's the thing that looks like a big shield or a capsule on the side of the spacecraft. That's actually the antenna. That's how we talk to it. Now, if you look directly in front of that, there's a thing that looks like a box. And it looks like the lid is open. It looks like there's a bunch of wires coming out of it. It looks like it has two arms sticking up towards the ceiling. Everybody see that? Right? That's referred to as the avionics ball. I like to refer to it as kind of like the brain and the head of the spacecraft. So all the electronics, like the computers, all the stuff that's running all the experiments and stuff, they're all located inside that box you see there in the front, right? Now that box is specially shielded and designed to protect against that radiation I just told you guys about. So all the big main components of the spacecraft, all the critical electronics parts, they're all located in that box, okay? And as you can see, the lid is open right now because they're still working on it. Now, if you look towards the rear of the spacecraft, you'll notice there's like little square red boxes, and then just behind it, it looks like there's red octagonal covers protecting 4 corners of the spacecraft. Do you guys see those? So all the red things you see are actually covers protecting critical components of the spacecraft. For example, at the very rear, the thing looks like octagonal covers are actually protecting the thrusters. Those are the thrusters in 4 clusters. It has 24 thruster engines, orientation engines, and they're in clusters in 4 locations in the corners right there. And the red covers you see on there are protecting them because even those are some of the first things they finished building. And the thrusters are super delicate because if you bump them, if you even bend them even just like a millimeter, when you get them into space and you turn them on, it'll make the spacecraft go sideways, right? It'll go the wrong direction. So they're very careful about this because they need to be exactly precise so that we know they're moving the right direction when they get into space. So that's why they're protecting them. So all the parts that have red covers on them, those are all critical components of the spacecraft. If you could go up close and look at all those red covers, all of them say remove before launch, right? So when they launch this, all those red things, they actually come off, okay? Now, although I mentioned to you guys, this is scheduled to launch in October of next year. Even though it's scheduled to launch in October, these people working on it, they have to be done by sometime in April or at the latest late May, right? And the reason for that is once they're finished with it here, they have to test it to make sure it's working. They have to clean it, then they have to pack it, then they have to ship it to Florida. Once you get to Florida, they have to unpack it, they have to clean it again to make sure nothing got dirty while they moved it. They got to test it again to make sure nothing got broken while they moved it. Then they got to pack it in the pointy part of the rocket. Then they got to take that pointy part, stick it on top of the rocket. You can imagine that entire process is pretty complicated. It takes them usually about 6 months, if not longer. So the reality is, if we want to launch in October, these guys have to be done sometime in May so they could ship it down to Florida and still have enough time to do all those things and put it on the rocket and launch it within the time frame that they need to, right? So although technically they got till October, the reality is these guys only have until May to finish this, so less than a year to finish this and have it shipped down to Florida. Okay?
And what are their titles?
The job titles of the people
Yeah,
here?
yeah.
So the question is about the titles of the people actually working in the room. Most of the folks that work in this specific facility are going to be engineers of some sort. The scientist folks are more involved in the back end once it gets to where it's going. So the folks in the front end, like where they're building and designing it, are going to be engineers. Now they could run the entire gamut of different kind of engineers. You could be a thermal engineer.
Astronautical.
Well, some of it could be a thermal engineer, electrical engineer, mechanical engineer, aerospace engineer, or it depends on what their specialty is and stuff, right? So then we'll also have some technicians here. Like for example, a computer programmer. They don't necessarily have to go and get a college degree because they can go programming certificate and stuff, right? So some folks might not necessarily have a degree. They'll have a certificate.
And Europa's not a solid. Is that a solid moon?
Oh, it's solid.
Oh, it is solid.
Yeah, it's like an ice ball with a like a wet.
Because they're not going to land on it yet.
Well, that's a great question. The question was, are they going to land on it? Now, that's a great question because depending on how you look at it, the original design of this spacecraft goes back nearly 20 years, actually. They've been proposing this program for almost 20 years now. And in the original version, they had an orbiter with a lander and a submersible. But when we proposed that, NASA was like, do you really think you can actually do that? Right? So, and we have to go convince Congress to give us funding to do that, right?
While you're out there.
Well, that's what we're thinking. We're thinking is we only get to go there every couple of decades. You might as well get
$1 billion
the.
to fly there? You
Well,
might as well try it.
the thing is, we want to get the most bang for the buck, right? If you're going to spend billions of dollars, you might as well get everything you can from it. But their attitude was, well, we're only going to get you that if you know for sure that it's going to work. And because we can guarantee it's going to work, they would fund, well, they wouldn't fund it. So the design kept shrinking. It became from an orbiter with a lander and a submersible. It became an orbiter with a lander, and then next thing you know, it only became an orbiter, and it became a limited orbiter in terms of what we can do, right? So this version is what they allowed us to get funding for. Right, which is just the orbiter portion. And the thinking is, if this works and we can gather enough information, then we might be able to convince them to let us send a lander and do the other stuff, right? So
potential to be ready.
Well, yeah, we would love to do that, but they didn't give us funding or okay to do that, right? So, that's the thing, right? So with that, the question was, how much does it cost, right? Well, this thing, once they send this thing into space and they get it up, this is going to be the most expensive mission JPL has ever done. Right now, most of our missions are usually in the several $100 million range. If it's a big, quote-unquote, Cadillac mission, that's like the Rovers or something very, very big like Cassini, they might cost $2 billion. The most expensive current missions that we have are right around the $2 billion range. This one, once they get into space, is going to be roughly about $5 billion. So it's going to be the most expensive mission we have actually sent out, right? And by the time they send it in space, when they get this thing up there and it pops open, they have the solar panels open, just like what you see in a model. From one edge of the solar panel to the other edge of the other solar panel, from edge to edge, it's over 100 feet wide, right? So if it was in the room here and we opened it, it wouldn't fit the room. It would be too big, right? Because the wings would go right through the walls here. It's too big. It will be the largest spacecraft JPL has ever sent to space once we get it up next year. happens is this main room you see here, we call this the DSOC, Deep Space Operations Center. And it's the central hub of our entire communication network. This is the main mission control room. This room feeds to each of those smaller mission support areas. So all the miniature mission control rooms are all connected to this one main room. This main room is the central hub of the entire network. Everything goes through this room. This room runs 24 hours a day, 7 days a week, 365 days a year. It's been running nonstop since the first day they opened the doors in 1964. So this room has been running nonstop, communicating with spacecraft since 1964. Every single deep space robot NASA mission has been conducted from here. Okay, so I'll let that sink in for a second. If it's a NASA mission, NASA built it. It's a robot, right? And it went to deep space, meaning it went to the moon or further out in space. That mission was run from here. We sent, received, controlled the signals from right here. All the cool discoveries, the pictures, whatever it found, that data, it came through this room, right? So that's why it's a National Historic Landmark. In its history, it's been used to communicate with somewhere close to around 300 different spacecraft. Right now, we're using it to talk to anywhere between 30 and 50 missions in space, depending on the day, right? So that's why it's such an important facility here. In fact, we don't use it just for our missions. Other countries will use this facility for their missions as well. For example, the Indian government built a spacecraft called the Mars Orbiter mission. You guys might have heard of it. We actually refer to it by its acronym MOM, right? The Indian government built it, they launched it, they sent it to Mars. The problem was they don't have installations like we do. They couldn't talk to it, they couldn't control it properly. So we actually assisted them with communicating with their spacecraft, helped get it to Mars, helped get all the data and all the images and all the information back from their spacecraft to them, right? And they used our facility here. What I'm getting at is basically we use this not just for our missions, we use it for everybody's missions, right? Pretty much just about almost everybody around the world pretty much uses this facility to talk to their deep space spacecraft, okay? Now, this room is connected to a bunch of giant antennas we use to send the signals. And if you look over here, here's a silhouette of the antennas to give you an idea of how big they are. This is our largest antennas we use. We call them 17 meters. That means from one edge to the other, it's 17 meters across. To give you an idea of what that means, if you've ever been to the Rose Bowl or the Coliseum, seen a football game or a soccer game, you know how big the field is. This antenna is so big, it's wider than the football field, nearly as long. You could almost play football in the middle without falling off the edges. So if you guys have ever been to the Rose Bowl or Coliseum, you know how big the field is. This is almost as big as that field you've seen, right? That's how big it is. Now, on this picture, you can see there's a silhouette of the person down here to give you an idea of just how big the whole thing would be. We also have a bunch of small ones like this one. These are called 34-meter antennas, so they're a little bit less than half the size of the big one. And you can see there's a silhouette of the person there to give you an idea of how big those are. Now, the way it works, the further away you get in space, the larger the antenna we need to use. Something close by, we could get away with using something smaller. So the distance of the spacecraft determines the size of the antenna we need to use to talk to you. The further away you get in space, the larger the antenna we're going to need to be able to talk to you properly. Okay?